Good morning. My name is Huidae. I'm an associate professor in engineering. I think I have 30 seconds. Okay, I gave 2 lightning talks last 2 weeks. This is my third one. I have 24 slides. It's okay. And which one is it? This is, yeah. Right, so I think I can skip many of these theory about variant transport, and he gave a really nice intro. And let's talk about some computational things here. So he does all these lab experiments, and he gives me those experimental results. And what I'm doing with those results or his data sets is basically I'm simulating field scale variant transport using this model called Hydros 1D. 1D means it simulates vertical movement of contaminant. And I'm going to skip many of these slides. So this is a modeling setting here. This is a vertical soil column here. And we pour contaminant up here, and then we simulate this variant transport. And we have these boundary conditions. So we use lab settings for the boundary conditions, for example, concentration boundary conditions at upper level, upper surface boundary conditions, and 0 concentration gradient at the bottom. And we have these many parameters, and some of them are lab controlled, so we can fix them because we know what those values are. But the other parameters are unknown, basically. So we have 3 different approaches: optimization, which is deterministic modeling approach, and Monte Carlo, like uncertainty approach, and generalized likelihood uncertainty estimation, which is more statistical approach to this modeling project. So the first one is deterministic PSO. We use particle swarm optimization. This is a meta-heuristic optimization, which means it's a problem agnostic. So you can apply this optimization algorithm to any modeling efforts. So what this does is, you remember those unknown parameters, right? Non-lab parameters. So we have to determine the values of those unknown parameters. So we use this algorithm to find those unknown parameters, and from observe the breakthrough curve and control the lab parameters. So we have controlled lab parameters are as input, and then breakthrough curve as output. And we develop this objective function that we want to minimize. And by minimizing that objective function, by disturbing these unknown parameter values, we can find those unknown parameter values. But again, this is deterministic approach, and this is the result here. So red dots are kind of known or observe the breakthrough curve, actually artificial. And then blue line is the fit from Hydros 1D optimization. You see, it's pretty much perfect, right? But in real life, you don't really have perfect model, right? Because all models are wrong, right? And the only question is, how can you make these models more useful? By estimating those parameters or doing something. So we do Monte Carlo simulation here. Monte Carlo simulation means, so all those unknown parameters, we don't know what values work best for your observed breakthrough curve. So initially, we have no confidence in any of those values range. Each parameter has a range, and we have no confidence or no belief on any specific value of each of those parameters. So initially, we have no confidence, so we assign, I'll show you that later. So we assign no belief, which means we have uniform belief. So we think, oh, let's say, for example, let's give a follow-up quiz or game, right? So we have these many people at airport, right? And then as a airport employee, you don't know who is more patient and who is less patient. So we give same attention to everybody. So that's prior knowledge because we don't know about these people. Now, people start getting angry and start getting complain about all these delays, then we know who is less patient. Then we give more attention. That is posterior knowledge. So we go from prior to posterior. That is Bayesian approach, and this is the prior step before that. So this is Monte Carlo results. Monte Carlo means we just disturb all these unknown parameters with no posterior knowledge, and then run these simulations 10,000 times, 100,000 times. This is the result, and black line is observed actual breakthrough curve from his lab experiment. And you can tell all these 10,000 simulations actually can enclose this lab experiment, which is good. And this is best out of 10,000 simulation runs. And this is a statistical approach. Now, prior to posterior, now we know who is impatient, right? We give more attention to them. So that's how you gain more knowledge about all these parameter sets. So this is a Bayesian theorem. So initially you have probability of your, let's say, your customers being patient. We don't know, right? We get same attention, same level of attention, and then you start getting complaints. Now you learn from those complaints and you revise your knowledge about those customers. And now you have posterior knowledge about your customers. That's a Bayesian approach. And we use this statistical function, probability function, which is normal distribution. And so this is prior. You see, it's pretty flat, right? So we are giving the same level of attention to all these parameter values because we don't know which parameter values are good for this parameter. And then this is our belief about our breakthrough curve or objective function. If error is 0, wow, this is good, right? When your error is 0, you give high belief or confidence. If error is greater than 0 or less than 0, negative, right? Negative errors, then we give less and less confidence. And based on that statistical model, we assigned likelihood to produce this cumulative distribution function that goes from 0 to 1. And you see this spike. The spike means this parameter value is really good. It can reproduce breakthrough curve really nicely. And then you can see other parameters, cumulative distribution function. And then this is what we are working on right now, soil scenario generation. So the main point of this hydrology modeling is because you can really test every single point in the lab. It's too expensive, and the scale is lab scale, small scale. So that's why we do all this modeling. And from here, we take a land cover data set from NLCD and soil data set from SOGO, and we combine them to generate some soil database like this. And then we have generated soil scenarios and compared with existing Rosetta soil data set. And they have similar patterns, but slightly shifted. And summaries, so we developed this modeling framework for 1D fed and transport modeling, and we optimized the model, and we conducted Monte Carlo simulations, and obtained 95% confidence interval using the glue approach, and created a soil scenario database. And we will conduct more analysis, including sensitivity analysis, and we'll analyze more lab data sets as they come, and then analyze artificial soil scenarios based on this soil scenario generations. And one of our maybe very ambitious goal for next year is to develop this easy-to-use, user-friendly GIS plugin system. So you can just, it's like a Google map, right? In a map, you just draw your area of interest, and then it'll generate soil scenarios automatically and runs Hydros 1D 10,000 times automatically without you not having to know how to make Huidae 1D or soil generation. Everything is automated back end and then produces the same kind of results automatically. Thank you very much.